If I asked you to count to 31 using just the fingers on a single hand, you'd probably tell me I was out of digits. But that's only true if you're trapped by the rules of base 10 mathematics. To break out of that, we have this, a 3D printable binary abacus. It takes the invisible language of computers and puts it directly into your hands. The clever part here is the print-in-place design. It comes off the print bed as a single, fully functional object with zero assembly required, and the internal switches just snap back and forth with a satisfying click. But look closely at the labels along the bottom. Instead of our standard 1, 10, and 100 columns, we have 16, 8, 4, 2, and 1. To make this tool work, you have to completely throw out how you normally count. In this system, there are only two states, on or off. Let's establish the golden rule of base 2. The number 2 does not exist in its vocabulary. Every switch is either a 1 or a 0. If we start at 0 and want to count to 1, the logic is intuitive. We just go to the far right column and flip that switch to the on position. Here is where we hit our first mechanical roadblock. What happens when we need to add another unit to make 2? That 1 slot is already full. We handle it the exact same way you carry a 1 in normal addition. You reset the first column to 0 and push that value over by flipping the 2 switch. This creates a continuous cascading effect. Every time a column hits capacity, it resets and forces the switch immediately to its left to flip on. You don't have to memorize a complex code to count upward in binary. It is literally just a physical chain reaction of filling a slot and pushing the overflow to the left. That bottom-up method works, but what if you want to skip straight to a larger number, say a birthday like the 26th? You don't want to manually click through 25 carries to get there. Instead, we can play a simple top-down subtraction game. We look at the largest available label on our abacus, 16, and ask a basic yes or no question. Does 16 fit into 26? The answer is yes, so we flip the 16 bit to 1. When we subtract that 16 from 26, we have 10 left over. Then we move right down the line. Does 8 fit into our remaining 10? Yes, so we turn it on, leaving us with 2. Does 4 fit into 2? No, so we skip it. Does 2 fit into 2? Yes, it fits perfectly, leaving us with 0. Because our remainder is exactly 0, we simply leave that final 1 bit switched off. Read the pieces from left to right. 1, 1, 0, 1, 0. We just physically generated the exact binary code for 26. This does-it-fit subtraction game is the exact same logic a computer uses to rapidly sort and allocate data into active memory. Of course, a 5-bit block has a hard ceiling. By flipping every single switch to 1, you max out at exactly 31. To go higher, you just need a bigger board. That's where the expansion module comes in, continuing to double the place values to give us slots for 32, 64, 128, up to 512. By snapping these two blocks together side by side, we apply those exact same subtraction rules to map out much larger numbers. Let's try 855. Running the subtraction down the 10-bit line gives us 11010101111. Doubling the bits from 5 to 10 jumps our maximum value from 31 to 1023, showing how binary systems accommodate large numbers with very little physical growth. These modules turn binary code into a tactile game of carrying and subtracting. Looking at this vibrant, multicolored collection, you realize that real computer science doesn't have to look intimidating. Whether you're a teacher, a parent, or just a curious student, the print-in-place file is incredibly easy to download and set up. Load up your favorite filament color, print one out, and try challenging a friend to a binary guessing game. Demystifying computer science doesn't always require a screen. Sometimes it just takes a tool you can hold in your hands.